shear force and bending moment, okay, and bending moment using integration method. Okay, we're going to use the integration method. So in order to use the integration method, we have to know, okay, to use, so if integration method means what? We're going to use dv over dx, right? We're going to use dv over dx, and we're going to be let it equal to minus omega as a function of x. Okay, so on this problem, I do apologize. You have 6,000 at one end, Newton. At the other end, you have 18,000. Okay, right? So we're going to use dv over dx minus omega x. In order to use the integration method, right? The first thing we have to find, so the first thing we have to find the function of the distributed load. Okay, we have to find the function of a distributed load. Then from here, we're going to do our first time. Okay, so once you identify a function, so we have omega as a function of x done already. Okay, then we have to integrate your first integration. When you have done your first integration, you have v as a function of x integrate minus omega as a function of x dx plus by c1, right? Where c1 is a constant. And then you let the whole thing to be equal to dm over dx. Then you integrate again for the second time. So you have moment as a function of x. You integrate twice minus omega as a function of x dx dx plus by c1x plus by c2. Okay, so c2 is also a constant, right? So for this case, we have to identify boundary conditions to determine C1 and C2. Okay, we need boundary conditions. So now I'm going to teach you how to determine boundary condition. Okay, so at point A, x is equal to 0. So datum is always on the where? On the left-hand side of the structure. Okay, I repeat again, the datum is always on the left-hand side of the structure. So on the other side, you have x is equal to 6 meters. Right? So there are a sequence of boundary conditions that I want you to remember, okay? Which is V, M, theta, Y. Likewise over the other side, V, M, theta, Y. So you know that V is shear force, M is moment, okay? Theta is the slope. I'm not telling you the slope yet, and Y is the deflection. Okay? And when at x is equal to 0, right? The shear force is equal to what? 0. Why the shear force is equal to 0? Because the beam is allowed to what? It's allowed to deflect. Okay. When x equals 6, shear force is not equal to 0, but we know that the shear force is what? Maximum. Okay. Now, next we look at the moment. Can anyone tell me when x is equal to 0, what is the moment equal to? Is it equal to the 0? If yes, why? Thank you. Anyone? Can you remember? I hope you all can hear me, right? Okay, so you all cannot remember, but I will tell you moment is equal to 0, right? So why moment is equal to 0, right? So if you look at B, sorry, you look at point A, and if we were to remove B, what will happen to the structure? The structure will want to what? Rotate, yes or no? Right? There's no resistance, right? If there's no resistance, force is equal to 0. Likewise, over here, YV is equal to 0 because it is allowed what? You allowed it to move, okay? So slope we don't know yet. Deflection is definitely not equal to 0, okay? Now let's look at when X is equal to what? 6 meters now, okay? Moment we know is not equal to 0 because moment will be at its what? Maximum, okay? I will not talk about slope yet, but we know that deflection is equal to what? 0, okay? So one thing to observe is at point B is where the structure will fail. If this thing will be under load, point B is where the structure will fail, right? So now, why the moment at point B is, there is a moment is not equal to 0, okay? Let me explain. So now, if we were to remove, or we were to remove the support at A, right? Is the structure rotating? The structure for this case is not rotating. Why? Because we have a what? We have a counter moment over here. Moment at point B, right? We have a counter moment. That's why the structure is not rotating. That's why our moment is maximum. Where at point A, the moment is equal to 0 because when we take away the support at point B, the whole structure will what? Will rotate for that reason. Okay. So what we have done down here now, okay, is we have identified, this is what we call our what? Boundary condition. That's why this topic is very abstract, yes or no, right? From the loading condition, from diagrams, we have to relate it mathematically what's going on. It's not like when you are doing your math, what happened? The question is always you have these numbers, solve for it based on this boundary condition. What it means physically is secondary. For this course, what it means physically is primary. The math is very easy to solve. Okay, so in math, you just care about, okay, how are you going to solve this? For this case, physically, you need to know because have we formed any equation yet? No, we have not formed any equation yet. Now is we have to form the equation. Okay, right. So we're going to form the equation. So now first thing we have to know is we have to find the function of the what? Of the distributed load. Okay, we have to find the function of the distributed load. Okay, so first we have to find our omega as a function of x. So I'm going to sketch this now. All right, so this is omega. This is your x. Right, so this is 6,000, 12,000, 18,000. Right, then you have your slope, you have your gradient down here. So this is your, and it stops down here, and it stops over here, and this is 6. Okay, so we know the function will be omega as a function of x will be equal to, so we find the gradient, right? So we find the distance from here to here is 12,000, and then the distance from here to here is 6,000, 6, right? So it's equal to 12,000 divided by 6x is positive slope, plus by the y-intercept is 6,000. Okay, so this is equal to 2,000 x plus by, is it 2,000? Yeah, plus by 6,000. Okay, omega is a function of x. So that's your equation number 1. Okay. So we're going to substitute. All right, we're going to substitute equation 1 into dv over dx is equal to minus omega as a function of x. So don't forget your what? Don't forget your negative sign, okay? Don't forget your negative sign. So I'm going to take the whole problem. I'm going to start on a new page. Okay. So we know that dv over dx is equal to minus 2000x minus by 6000. So when we integrate, okay, so v as a function of x will be equal to minus 1000 x squared minus by 6000 x plus by c1. Okay, plus by c1. So this is our equation number 2, right? So now we have a function. Now we are integrating now, right? So now we are going to substitute when x is equal. I'm looking at my boundary condition now. Okay, so we can substitute when x is equal to 0, right? V is also equal to 0 into equation number 2, right? So where is this boundary condition? So if you look at the other page, okay, so that boundary condition is when x is equal to 0, v is equal to 0, okay? So when you have used a boundary condition, I usually have a very good practice that I am going to put a tick mark, okay? So I've used it already. You cannot use your boundary condition twice. You only can use it once to solve a particular set of conditions, okay? So from here, we know that, so therefore, C1 is equal to 0, right? So therefore, V as a function of x is equal to minus 1000 x squared minus by 6000 x, and this is your equation 2a because it evolved from equation number 2. Sorry, yeah, I forget another term. Okay, so what I forget is this. We know that v as a function of x is also equal to what? Dm by dx. Okay, so from here, m, you integrate again, m as a function of x. So now this is equal to minus 1000 x cubed over 3 minus by 6000 divided by 2, 3000x plus by c2. So now this is your equation number 3. Okay.
Oh, Eugene, do you mean 3000x squared?
Yeah. Thank you. So this is your equation number 3, right? So next, we're going to substitute when x is equal to 0 and your moment is also to 0, and we're going to substitute into equation number 3, right? So if you look at equation number 3, or the next boundary condition, it is basically this one we are using now. Okay, so this is the one that we're using. I'm going to put a tick mark. Okay, I've used that boundary condition. So therefore, C2 is equal to 0. Okay, so from here, m as a function of x will be equal to minus 1000 x cubed over 3 minus by 3001 x squared. Okay, so this is your equation 3a. Okay, so by this is solving or finding the shear force and bending moment equation just by doing integration. Okay, so now if we were to sketch, right, we were to sketch our shear force and bending moment diagram based on the equation. right? So this is our x. Then this is our, it can be our shield.